Hello students, this is the third video or third section of our module 4 planning of fundamentals of artificial intelligence course. In this session, we continue module 4 planning from the course fundamentals of artificial intelligence. In this part, we mainly focus on graph-based planning and conditional planning. So mainly these approaches extend classical planning and improve efficiency to handle uncertainty in the data. These are our contents, definition of classical planning, algorithms for planning with state space search and planning graphs, other classical planning approaches, analysis of planning approaches and hierarchical planning. Already we have looked into definition of classical planning, algorithms for planning with state space search and other classical planning approaches. Okay, so in this presentation, as I said, we mainly concentrate on planning graphs and conditional planning, in which these are the advanced classical planning approaches. As we discussed about planning in our previous video, planning is a course of action and which is a key requirement for an intelligent agent. And an intelligent agent must determine what actions to perform in what order in order to achieve a goal. So the right presentation for actions and states and the right algorithms make planning very easier. And also this reminds us that planning depends on mainly three factors, that is how states are represented, how actions are represented, and how search is performed. These are the things which we already saw in our previous videos. So now in this slide, we will see what is graph-based planning. Okay, so this is a type of classical planning approach which was introduced in 1995 by Blum and First. It builds a planning graph and extracts a valid plan using mutual exclusion, which is also known as mutex. So it is mutual exclusion reasoning. So, graph-based planning constructs a layered structure called a planning graph. This structure alternates between two levels. They are preposition levels and action levels. So, prepositional levels is also known as S levels, and action levels are also known as A levels. So, preposition levels mainly represent states or the facts, whereas action levels represent applicable actions. After constructing the graph forward, the algorithm searches backward to extract a valid plan. And this approach combines both forward graph construction and backward plan extraction. This means that there are mainly two phases of graph-based planning, that is graph construction, which is phase one, and second phase is plan extraction. Now we'll see the structure of a planning graph. That is, a planning graph contains two levels and one relation. That is, first one is positional level, which is also known as S levels. That is S0, S1, and S2. These represent the set of all the literals that may be true at that level. Okay, and next one is action level, that is represented by A0, A1, and A2, and these are the set of actions whose preconditions are satisfied at the previous level. And now you have mutex relations, which is also known as mutual exclusion. And this indicate the pairs of actions that cannot occur together and prepositions that cannot be true together. Okay, so in a planning graph, we have two levels and one mutex relation. First one is preposition level, second one is action level, and third one is mutex exclusion or mutual exclusion relations. So in graph planning, you have two phases. First one is graph construction, and second one is phase two is plan extraction. Okay, now we'll see phase one, that is graph construction. Okay, so the graph planning algorithm begins by initializing the planning graph, in which the initialization is the first step, that is initializing of planning graph, in which S0 is equal to initial state. Okay, capital S0 is equal to initial state small s0. Okay, and once you initialize your planning graph, you have to add action level AI, which include all the actions whose preconditions are in subsets of SI. Also include the persistence actions called no-op actions. No-op actions maintain facts from one level to the next level. Okay. Once you're done with addition of action level AI, you have to perform the mutex relation between those actions. That is based on three conditions, that is inconsistent effects, interference, and then competing needs. Okay, once action level AI addition and mutex relation addition is completed, then we'll move on to the construction of next propositional level SI plus 1, in which we will add all the positive effects of actions in AI. Okay, and then again you have to add mutex relation between the propositions. That is, if all ways of achieving them are mutex, you will add mutex relations. Okay, and finally we'll search for goals. Okay, G is equal to goal state. That is, if goal G appears in SI plus 1 and no pair of goals are mutex, then you can go directly to phase 2. Phase 2 is plan extraction. And next one is, if graph levels are off, meaning no new neutrals are added, then you have to return failure. So in the graph construction, you will initialize your planning graph first, and then for each and every level until the termination, you have to perform some steps. First one is addition of action level AI, and then you have to perform mutex relation between those actions based on inconsistent effects, interference, and competing needs. And then you have to construct next propositional level, that is SI plus 1. And then you have to add mutex relations between the proposition, and then if goal state G appears in SI plus 1 and no pair of goals are mutex, if those two conditions are satisfied, then you can go to phase 2. Otherwise, if graph levels are off, then you have to return failure. So what do you mean by graph leveling off? Which means that expansion is complete and no further solutions exist. So now we'll see phase 2, plan extraction. This is nothing but backward search. So once we are done with phase 1 graph construction, we'll move into plan extraction. That is, in the first step, you have to start from the goal set at the last SK. Okay, and then in the step 2, select a set of non-mutex actions in AK that achieve all the goals. Okay, this is similar to the backward state space search which we discussed in our previous video. Okay, and step 3, for each selected actions which you are performing, add its preconditions as new subgoals at level SK minus 1. Since we are performing backward search, that is equal to SK minus 1 steps. Okay, next step 4 is that repeat this backward process until we reach our initial state, that is S0. S0 was our initial state in our phase 1 or the planning of the graph. So if successful, then you can return the plan. Otherwise, you can backtrack and try any other combinations. Okay, when you're doing the backward search or backward extraction or backward plan extraction, you can finalize that your plan was successful. Thus, planning graph construction is forward and planning extraction is backward. So I will explain these inconsistent effects, interference, and competing needs with a simple layman example. Okay, so for inconsistent effects, consider two actions, action A and action B. Action A is turning on the light and action B is turning off the light. Okay, so if you try to do both at the same time, it will not happen, right? They contradict each other. So these two actions are mutex or mutually exclusion conditions. And second one is interference. Okay, again, two actions. First one is you study in a quiet room, and action B is play loud music. Okay, so in this case, playing loud music removes the quiet condition which is needed for studying. So you cannot study and play loud music at the same time, right? So they interfere. This is mutex actions. Next one is competing needs. Again, consider two actions. That is action A, that is you are going to cook food. What is the need? Gas stove should be available. In action B, iron clothes. Need will be same plug point or some power socket should be there. If both need the same limited resource, they compete each other. So you cannot cook and iron using the same single resource at once. So these conditions are also again mutex. Okay, in simple words, mutex means that two things cannot happen together. Now we'll see this graph planning concept with a simple example. You have initial state, goal state, and some actions. So initial state is that at home and you have a car and your goal is to reach the office. So in order to reach from your initial state to goal state, what are the actions you should perform? That is, you should drive from home to the office. So what are the preconditions? You should be at the home and you should have a car. So addition operation, that is at office, and deletion is at home. At home is the precondition or the previous action. Okay. So what are the three steps available? You have S0, that is S0 is your initial step in which at home and you have a car. Whereas in step 2, that is A0, what are the actions you are going to perform? So you are going to drive and know of actions. Next one is step 3, that is S1, your next state. That is you are at the office and you have a car. So here in this case, since the goal appears in S1, what is your goal? At office, right? So that goal appears in S1, so we can extract that plan. The plan is simply you are driving from home to the office. So this example demonstrates how planning graph builds level and extracts the plan. In this slide, we will quickly summarize what is graph-based planning. So graph-based planning is a type of classical planning algorithm which constructs a layered planning graph consisting of preposition and action levels. So mutex relations prune incompatible actions and states. You have two levels, that is preposition level and action levels. And the mutual exclusion relations will prune or delete the incompatible actions and states. Once the goal literals appear without mutual exclusion, backward search extracts the plan. You can say that graph plan is complete, sound, and efficient for classic deterministic planning of the problems, and it significantly reduces search compared to naive forward or backward state space search. And as we discussed earlier, in graph-based planning, there are two phases. First phase is graph construction, and second phase is plan extraction. In the previous slides, we saw about graph planning, right? So from this slide, we'll be mainly concentrating on conditional planning algorithm. So conditional planning is mainly used in two environments, that is non-deterministic environment and partially observable environments. In such environments, actions may have multiple possible outcomes. The agent may not know the exact current state. A single linear plan is insufficient. Okay, so instead of producing a sequence of actions, conditional planning produces a simple plan tree. So this tree can contain action nodes, observation branches, and different subplans for different outcomes. So let me explain this with a simple example. So planning to go to college with uncertain weather. Okay, so there are mainly two possible outcomes. That is, it may rain or it may be sunny. So one single plan will be by just go by bike. Okay, but because of the weather condition, it is little bit risky. So what you will do, you will make a conditional plan or plan tree, that is check whether two possible conditions, that is if it is raining you can take the bus, or if it is sunny ride bike. So now we'll see the detailed description about conditional planning algorithm. It also has two phases, that is OR search and search. So it tries to find a plan that works for all possible outcomes. So instead of thinking about do this, then this, what it will create, if this happens, do this, else do that. This is simply a if-else statement. Okay. So in this algorithm, you have the first function as OR search. So if states satisfy the goal, then return success. It means that if you already matched or reached your goal, you don't need to do anything more. For example, if you want to reach home, if you are already at home, then the algorithm stops. Okay. So in the second step, if state is in the path, return failure. Okay, this means that if you come back to a state you already visited, then stop. This is to avoid the infinite looping. For example, you go from room A to room B and then room A again. So this is a kind of loop, right? So stop this path, okay, in order to avoid the looping condition. Step 3, for each action applicable in the state, try each possible actions and if see if it can lead to a particular solution. So this means that an action can have multiple possible results. So you must check and do all the possible results of the actions in order to reach your goal. So if no action works, then return failure. If every possible action fails, then no plan exists. So this slide mainly shows and search in the conditional planning algorithm. So as we discussed earlier, there is or search, that is it chooses an action, whereas and search checks all the possible results of that action. So in simple case, or means which action should I try, and means will this action work in every possible outcomes. So the step one is that for each possible outcome, state S in states subplan is equal to or search S path. If subplan is equal to failure, then return failure, which means that for every possible result of an action, try to find a plan from the. For example, action is you are going to check weather, and you know that there are mainly two possible results, that is rain and sunny. So it tries out the possibility or search rain and or search sunny, the states. Okay. And in the step 2, return condition plan that combines all subplans for each outcome. So before that, if subplan is equal to failure, then return failure. This means that if even one outcome cannot reach the goal, then this action is not at all safe. For example, if you are considering that rain, okay, no way to reach college, sunny, then reach college, okay, so then whole plan is a failure. Whereas in the step 2, it written that return conditional plan that combines all subplans for each outcome. If all subplans is succeeded, then return the conditional plan. If rain, then you can take the bus and you can reach the college. If it is sunny, you can take the bike and then you can reach the college. So this is a type of conditional plan. Now we'll see an example for conditional planning algorithm. The problem statement is that a robot wants to cross a road. And what are the actions you have to perform? Actions are check traffic and cross road. And for check traffic, you have two outcomes, that is road clear and outcome 2 is car coming. Then if it is safe, then cross road. That is works only if the road is clear. So this means that crossroad works only if the road is clear. So the conditional plan mainly becomes first you have to check the traffic and then you have to check the two outcomes. That is, if road is clear, cross road. If car is coming, you should not cross the road. So this forms a plan tree rather than a linear sequence. So, as we saw earlier in the previous slides, conditional planning extends classical planning. It handles two actions, that is, non-deterministic actions and uncertainty. It generates a conditional plan tree, and OR nodes represent action choices, and AND nodes represent the multiple possible outcomes. So the algorithm is complete but computationally expensive due to the exponential branching. In simple terms, you can tell that conditional planning is somewhat like if then else rules. So in this video, we discussed mainly about graph-based planning and conditional planning. In graph-based planning, again, you have two phases, phase one and phase two, that is graph construction and plan extraction. And in the conditional planning, again, you have two searches, that is AND search and OR search. So as a summary, you can tell that graph-based planning improves efficiency in deterministic domains, whereas conditional planning extends planning to uncertain environments, and both approaches enhance the capability of intelligence agents. So thank you.